All right. Hello, everybody. Hope everybody's doing well. This is the second to last week of classes. We've got one more unit to go through, so let us do that. Before I start talking about Unit 9, as usual, are there any questions, comments, anything math that you want to talk about before we dive into Unit 9?
Can we talk about what the final's going to look like and final prep and stuff?
Nope. So, sorry, I only want to say one thing now, which is I'm going to talk about the final next week because I want to make sure that I have clear in my mind what all the rules are, and so we'll talk about it either Thursday or next Tuesday. But I'm not quite ready to talk about it today. Is that okay?
Yep.
I've started thinking about it, and I have a good idea of how I want it to be. But I want to make sure that I don't tell you something today and then I change it on Thursday. So I will make a formal announcement, and I'll probably also send out an email so it's in writing for everybody. Yeah. But of course, it will be a take-home final because that's how things work now. And it will be available for several days. That's what I can already say. No, it's not going to be a final where you have a short amount of time. Cool. Any other question?
I'm a little confused on the difference between a quotient set and a partition. Or
Okay.
is a quotient set just a partition of equivalence elements, equivalence classes?
Yeah, so every time you have a partition of a set X, right, which means you break up X into disjoint subsets, right, then the quotient set is another set that has, for each of those subsets, just one element, right? So suppose, for example, that, we have the set of people in our class, right, and we partition them by our nationality, time of birth, right? Then, all the people that are born in the United States become just one element in the quotient set, right? I was born in Italy, so my nationality is Italian. I will be another element in the quotient set. I'm assuming that nobody else was born in Italy in this class, or is there any compatriot? No? Okay, so that would be the case. Does that help?
Yes.
Okay, great. So the subsets of a partition become the elements of the quotient set. That's the thing to keep in mind.
Okay.
Cool. Any other question? Is this? And sorry, let me say one more thing. The other thing is, so an equivalence relation, right, is a rule, right, is what allows you to decide what elements are equivalent. For example, the rule that says two elements are equivalent if they were born in the same country, right? So that the equivalence relation is the rule, and the equivalence relation allows you to create a partition, right? Because once you know what the rule is, then you say, okay, well, there is a subset of all the students that were born in the US. And then there's another part of all the people that were born in Italy. And then another part of, whoever might be born in whatever other country. Okay. So equivalence relation allows you to construct a partition. Once you have a partition, the subset of a partition correspond to elements in the quotient set. Cool. Yeah, so this week, I'm just reading the chat that Berkeley put on the chat. So this week, there's a bunch of definitions that seem very similar. So I wanted to start out by just kind of like reviewing some of the things that were in the little movie on Unit 9. And I want to do it by kind of asking questions and have you answer, and then we'll discuss the answer. Okay, so let me share the screen here. Desktop share. Let me figure out a way to pop out the chat, and here we go. All right. All right. So I've created a few questions here that I would like you to respond on the chat. The first question is a true-false question, right? And I'm asking, suppose that you have a function from x to y, an equivalence relation on y, and then the statement is that the prescription, the rule, square bracket f of x is equal to square bracket of f of x, always defines a function that we're calling square bracket f from x to the quotient set of y, mod equivalence relation. So take a second or two, and when you feel like it, put a T or an F in the chat box. Okay. See a few. Okay. I see a lot of Fs. A lot of people that don't believe this statement. Okay. So let's see. Let me pull out a little bit of space here, and let's parse this statement, right? So suppose I have a set x, and I have a set y, and I have a function between x and y. The function does not need to be injective or surjective, so let's make it neither. Go here and here. And we have an equivalence relation on y. That I'm drawing in red. Okay, so if I have an equivalence relation on y, I get a quotient set. And I have a projection function that I'm going to draw in blue. Well, so sorry, the quotient set has 3 elements. Let me call this U1, U2, U3. So these are going to be U1.
What does the square brackets mean again?
So square brackets means the equivalence class of, right? So this square bracket right here is just a definition. So this has no meaning yet. Right? And this one is the one that has meaning, and it means the equivalence class of. Okay? So the meaning of the square bracket around the letter f, the function f, is that we're trying to construct a function from x to y mod tilde, right? So what we're trying to do is construct a function here, and if it works, we're going to call that function square bracket f. right?
And just to be completely clear, the y slash Matilda means just that it's an equivalence relation.
So tilde is the equivalence relation. Y slash tilde, this is the quotient set. And so I wish my... And so you see that this set Y mod tilde has one element for each subset in Y, right? U1 is a subset that contains two elements in Y, it becomes just one element in Y mod tilde. So what does it mean that I want to send? So if X is my input, what does it mean to send it as an output to the equivalence class of f of X? So given that f is a function, do I have any problem if I take an input X to have a unique output f of X? No, right? Because f is a function. Then once I have f of X, if I say take its equivalence class, do I still just get a unique output? Okay, now that we've discussed this for a second, do people want to try again to answer the first question? Remember, the question is, no matter what f is, no matter what the equivalence relation is, I can always find a way to go from an element in X to an element in Y mod tilde by taking the equivalence class of f of X. And this will give me a function. Very good. So to Heidi and Paul and McKenna, yes, this is true, right? And answering Sarah, so it's absolutely true that no element X in X goes to U3, right? But this is not a problem with this being a function. This is just saying that in this particular case, this function is not going to be surjective. Okay. So I'm going to answer Berkeley's question in a second. Before I do that, Sarah, does that clarify your question? Can you tell me a quick yes or no? So the answer to your question is that the fact that no element in X goes to U3 is not a problem with square bracket f being a function. It just is telling me that this function is not onto, is not surjective. Okay. So answering Berkeley's question, right? So what the function square bracket f is depends on the partition, of course, right? Because if I change my red bubbles, then of course, suppose that I make one big red bubble that has U1 and U2 all together, then I would have only one element here in the quotient set instead of U1 and U2, and all three elements of X would go to the same element, right? but it does not change the fact that we have a function. Still confused about exactly what we're looking for? Yeah, so what we're looking for is, given the datum of a function from x to y, which is these green arrows, right? And given the datum of an equivalence relation on y, which gives me in particular these red subsets and these blue arrows, right? The question, is there a natural way by using this data to go from the set x to the set y mod tilde? And what this formula right here that I'm highlighting right now is saying, it's kind of a complicated way of saying, to go from x to y mod tilde, first follow the green arrow to get to f of x, and then follow the blue arrow to get to the equivalence class of f of x. Okay, so in a sense, the point of this question is, if you have an x, a y, a function between x and y, and a equivalence relation of y on y, you can always naturally get a function from x to the quotient set simply by following the arrows. Cool, great. Okay. And of course, yeah, so if you change the f, the final result is going to change. If you change the equivalent relation y, the final result is going to change. What's not going to change is that you're still going to be able to get a function. Great, so let's move on to the next question, which is very similar.
Wait, but how does it get to the ones that aren't touched by x? Like, what about U3?
Oh, but why do you want to get there? Right? So a function, right?
Because
the rule for a function is, for every input, you have to have a unique output, right? It doesn't mean that every element in the output set needs to be the output of some input, right? When that happens, we say that a function is surjective, right? But so what we're seeing right here, let me actually write it. In this case, f is not surjective, is not onto. Right? And precisely because U3, right, there's no way to get from an element to x to U3. But that's, that's okay. Rules that assign to one input, one output are functions even if they're not onto. Okay? Very good. So now we're going to ask the same question, right? But now the equivalence relation is on x, right? So we have an equivalence relation on x. I'm going to say, okay, now what we want to assign to the equivalence class of x, if the equivalence class of x is an input, we say f of x is going to be the output. And is it true or false that this rule always defines a function from the quotient set of x to y? Okay, can you please take a vote or true and false in the chat? Right now I only see Nathan. No, Heidi, Tyler, okay. False, sure. So keep answering while I draw the picture, and then we'll see what's going on, right? So right now, I start from an X, I have a Y, again, I have a function from X to Y, maybe here, and maybe here. And now I have an equivalence relation on X, maybe this one. So that now my quotient set has only two elements, and my projection function is like so. Okay. And so notice that now my inputs are down here, right? And what I'm trying to say is saying, okay, where do I send the equivalence class of X? Well, send it to f of X. So what could the problem be? The problem is that for this, say that this is, that X is equal to this element, let's call it smiley, then its equivalence class is this dot right here. This is the equivalence class of smiley. But if now I take X to equal this element over here, let's call it frowny, the equivalence class of smiley is equal to the equivalence class of frowny. But f of smiley and f of frowny, so this is f of frowny and f of smiley, are different. Okay? So in this case, this statement is false. And the issue is that we're trying to follow some of the arrows backwards. And following arrows backwards gives us a choice. You know, if I'm starting down here, I can go up to smiley, I can go up to frowny. And if this choice then lands me in different places in Y, then we have different outputs for the same input, and that's not a function. Okay. Is this clear to everybody? Yes. Okay. Thanks, Paul. Thanks, Sarah. All right. So it's not always possible to get a function that goes upwards and then across. But, well, maybe if we ask something of f, then we can make it work. Okay? So here's the third question, and this is a choose between a and b. Right? So here's the question. Now we have a function f from x to y, an equivalence relation on x, and we want to send the equivalence class of x to f of x, and we say that this rule, this defines a function from the quotient set of x to y, if and only if, which one of these two conditions is correct? The first one is saying if x1 is equivalent to x2, then it must follow that f of x1 is equal to f of x2. And the second one says that if f of x1 is equal to f of x2, then x1 is equivalent to x2. Choose between A and B if you can. Okay, great. I see that a lot of people are choosing A, and A is in fact the correct answer. Okay. Because, well, this is basically saying that if you have two different elements that are in the same bubble, in the same red subset, well, that means that in the quotient set they become one element, and therefore they better be sent to only one output, right? So this is the condition. Okay. Great. Cool. So now I want to complicate things a little bit. I'm going to go in a situation where you have, X and actually instead of N. Oops. Okay. Let me say, suppose we have an equivalence relation on X. Let me call it tilde X, an equivalence relation on X, and an equivalence relation tilde Y on Y. Okay. Then, which one of these rules defines an equivalence relation on the Cartesian product on X cross Y? And let me give you two options. X1, Y1 is equivalent to X2, Y2, if and only if X1 is equivalent to X2 and Y1 is equivalent to Y2. B, X1, Y1 is equivalent to X2, Y2, only if X1 is equivalent to X2 or Y1 is equivalent to Y2. Okay, so now, while you think about it, let me draw a couple pictures. Say that this is my X. This is my Y. My equivalence relation on X maybe is this one. My equivalence relation on Y maybe it's this one. And then I have my x cross y. Okay, so I see a bunch of A's, but now I don't remember if these are people that answered the previous question or not. But if we go with A, let me draw this in blue, right? Then the equivalence relation to the rule is telling me that we're only going to be equivalent sorry, and so if and only if I want to be careful. Here. Okay, so A gives me this partition, but let's give some names here. Let me call this x1 and x2, and this y1, y2, and y3. So A seems to give me an equivalence relation. Right? On the other hand, B, well, so x1 is not equivalent to x2, right? And y1 is not equivalent to y2. Okay? So therefore, it should be the case that x1, y1 should not be equivalent to x2, y2. Okay? Because the prescription tells me that for two pairs to be equivalent, either x1 is equivalent to x2 or y1 is equivalent to y2, right? And in this example, I've created it so that x1 is not equivalent to x2 and y1 is not equivalent to y2. But now, let's look at what this prescription B tells me, right? So x1, y1 is equivalent to x1, y2. Why? Because, well, certainly x1 is equivalent to x1. And we only need one of two of them to be equivalent, for the pair to be equivalent. It's equivalence relation. And then, well, but then x1, y2 is equivalent to x2, y2. Again, because now y2 is equivalent to y2. And if B were an equivalence relation, then we would have that by transitive property, right? It implies that x1, y1 should be equivalent to x2, y2. And so now we have a contradiction, right? Because we want simultaneously x1, y1 to be and to not be equivalent to x2, y2. Okay. this make sense? I hope so. Yeah, great. Because now I wanna get to the question that we had on the slides, which is suppose that I have f from x cross y to z, and I have equivalent relation on x, on y, and on z. And what I want is I want to obtain a function square bracket f from x mod tilde cross y mod tilde into z mod tilde. And the statement is, well, first of all, how do I want to define this function? The rule is that I want to assign to a pair the equivalence class of x and the equivalence class of y, the equivalence class of the pair xy. And the statement is that this is a function if and only if the following condition holds: if x1 is equivalent to x2 and y1 is equivalent to y2, then f of x1 is equivalent. Sorry, I have two inputs now. F of x1, y1 is equivalent to f of x2, y2. Okay, so I encourage you to do some examples on your own and become friends with this condition, right? But in a sense, this is just combining two simpler things, right? One thing is how to get a quotient function when you have a function from x to y and an equivalence relation on x and an equivalence relation on y. And the second thing is how to get an equivalence relation on a Cartesian product of two sets when you have equivalence relation on x and on y. Okay, I'm seeing no questions yet, so let me move on. I want to explain why did I want to care in particular about, if this is just a special case of just combining, two things that we already know, why did I want to frame this in particular, right? Because a particular case of this scenario are operations. In other words, what is addition? Well, in this language, addition is a function from Z Cartesian product, say addition of integers, let's keep it simpler, right? It's a function from the Cartesian product of the integer with itself to the integers that if you give me as input a pair m and n, produces the output m plus n. Similarly, what is multiplication of integers? It's a function from the Cartesian product of integers to the integers, such that if you give me two inputs, m and n, produces as an output the product, the number m times n. Okay, so operations are functions. Right? But they're functions from the Cartesian products of numbers with themselves to numbers. Does this make sense? Give me a quick yes or no, please. Because otherwise it's about to get even more confusing. Okay, great. Thank you. Thank you very much. So I want to go all the way back to the first day of class. And remember that during the first day of class, I asked and then left you hanging for the rest of the semester the question, what are numbers? Okay, and now I want to propose an answer that will at first look a little bit weird, right? But we'll see. We'll spend the time Thursday and next week to become more and more friends with that. Okay, so and the answer that I want to propose is that a system, first of all, there's not a universal notion of what numbers are, because we already know that we have different kinds of numbers. We have integers, we have rational numbers, we have complex numbers, right? So let me say a number system. So a system of numbers like integers or rational numbers or so on and so forth is a set X with two operations which we're going to call plus and times, but they may not have anything to do with our usual notion of plus and times. So let me put them in quotation. And so, what are these things if they have nothing to do with our plus? Well, they're functions from x cross x to x and functions, another function times from x cross x to x. And I have no idea how these functions are defined, but if somebody walks up to me with two functions, that they call plus and times from x cross x to x, then to know whether this person that is walking up to me has a legit number system, I have to ask, I have to require that this function satisfy all the usual laws of arithmetics. Right? So for example, I don't want to write them all because that would take us way too long. But one law of arithmetic is the distributive law, right? That x1 time plus x2 times x3 should be equal to x1 times x3 plus x2 times x3, right? This is the distributive law. So right now, we don't know what plus and times are, right? And so there's no reason a priori why the distributive law should hold. So if somebody comes up with some candidates for two operations, plus and times, on the set X, whatever X is, right? Then you have to check, if you want to promote this set to be a number system, you have to check the distributive laws hold. Right? Okay, so this is, again, it's a little confusing, maybe because it's turning on our head what we've been used to ever since we were kids, right? That we had numbers exists, operation exists, operations have properties. Now we're, doing a mathematical handstand, right? By saying, okay, we're not going to start from numbers existing. We're going to start by saying, let's take a set. Let's take some functions that we want to promote as operations. And if these functions give us operations that satisfy the rule of arithmetics, then we say, okay, we can call this set a set of numbers. Okay? So I'm almost out of time, but I want to just give a punchline, and then we'll work towards understanding this concept on Thursday in groups, right? But so the punchline is it's pretty hard to come up with number systems, right? So it's hard. With, let's say, new number systems. But we give you like a hopeful ending. Otherwise, if we were to stop on, it's hard. One technique, one way to do it is to start with a known number system something like Z or Q, or some numbers that we actually know, right? And define a good equivalence relation on it. And what will it mean for an equivalence relation to be good? It will mean precisely that will make the quotient set into a number system. Okay. And so this is the concept that we will explore in Unit 9 in the group work next week. And this is also going to be the main concept that I want to base the final on. So I would like to, encourage everybody to, spend some time between now and Thursday already to maybe look over what we said right now and, try to make some sense of it and try to already get a little bit ahead with me, come up about what is clear, what is not clear. And then, Thursday we'll work in groups. Next Tuesday, we will discuss it all together. And then the last Thursday of classes, I want to open it up to talk about this further and talk about the final, anything that might help with the final. And we'll go from there. So sorry, I'm a little bit late today, a little bit out of time, but thanks for your attention and see you all on Thursday. And I will post the video and I will share the link to the Blackboard. Cool. Have a good afternoon, everybody. Thank you.